Okay, so continuation with the Bezier curve with respect to the previous class. Okay, first let me touch upon few things and then continue. So the first thing is that for a Bezier curve, okay, so we are going to take 2 points, say for example P0 and P1, okay, which has to be connected by a continuous line or an arc. So since it is only 2 points where we can connect them by a straight line, okay, and writing this, uh, the formation of this line between these 2 points is actually starting from P0 and P1, right? So the control points are only these 2 points. So to represent this, it is in the form of only a linear equation, okay, because there are only 2 control points. So number of degrees will be n minus 1. So number of control points is 2 minus 1. So it's going to be only 1. Okay, so thereby it is going to be a linear equation. Okay, and coming to the basic understanding also, where each of these points have to be connected across the path from P0 to P1. Okay, so it is going to be a continuous straight line where the points are set one beside the other, and no need to find out any kind of tangent or any other weighted method. Now, when we come to the other thing where we have another point P2, and then what is going to happen is that we are going to have it like this. Then the curve has to start at point P0 and end at point P2, where the curve is going to take a turn, the tangent and the weighted method, all this is going to depend upon all these 3 control points, that is P0, P1 and P2, right? So now it is going to have a quadratic curve, okay, based, that is because it is going to depend upon the mathematical equation for this is going to depend upon the quadratic equation. Okay, so here number of points, control points is 3, okay, right, and number of degrees of polynomial will be, if we say that this is, so number of degrees of polynomial will be n minus 1, okay, so it is going to be 3 minus 1, so it is going to be 2. That means the equation will be in the quadratic form, okay, right? Degrees of freedom polynomial will be 2, that means quadratic. Now say for example, if we are going to have one more, I'm going to have one more point, then this particular thing is going to have a different portion altogether, like this, okay, right? So once it is going to be like this, so here we have totally 4 control points, okay, and the shape of the curve is going to be like this, which is actually going to depend upon the Bezier equation. We'll see that in the next step, okay, right? So for this, number of control points is going to be 4. Okay, so degree of the equation or the degree of the polynomial will be 4 minus 1, which is 3. That means cubical curve. Okay, so the curve is going to depend upon the cubic equation, right? Okay, so these things we have to remember, right? Okay, right. So now let us see about the equation and how it changes with respect to time, or how it has to be proceeded also. We'll see that now. Okay. Okay. So now coming back over here. Okay. So let's start from the basic thing. So we have only 2 points, which are the control points for the curve. So when we start connecting between 2 points, as we know, a curve always has to start at the starting point and end at the ending point. It cannot go outside this by skipping this starting and ending point. So it has to be there only. So here only 2 points are there. So the curve is going to start at P0, end at P1. Okay. And for this, when we proceed it, okay, it is going to be a straight line. Okay, right? So a linear equation can be written in the form of L0 of function of t, where it is equal to 1 minus t into P0, that is the starting point, plus t into P1. Okay, that is the P1 is the end point. Okay, where t is a function which varies from 0 to 1. That means, say for example, we can assume from 0% to 100%. So when we are going to start, we are going to start at P0, which is 0, and when we are going to end, it is nothing but 1 or 100%. We always take it as 0 to 1 in the range. Okay, so if it is going to be where t value is going to be 1, that means it has already reached the end point. If the t value is 0.5, then it is in the midway, right? So like that. Okay, so we'll see that now. So here we can see t varies from 0 to 1, right? So we'll just gradually see as the value of t varies, you can see that the line or the arc is going to be drawn. In this case, the line is going to proceed from P0. Okay, so where at this particular point, where it is approximately where the value is t is equal to 0.47. Okay, so what is the equation of the line? So L0 will be 1 minus 0.47 into P0 plus 0.47 into P1. Now, if we take a look at this before going to this, if we take a look at this, if T is going to be 0, 1 minus 0 is 1, 1 into P0, that means the P0 value itself. When T is 0 multiplied by P1, that is going to be 0. That means L0 is going to be the value of P0, nothing but at the starting point. Now, when the T value is going to be 1, okay, so where is the curve or the portion of the curve actually? So if you want to locate when the value of t is 1, so 1 minus 1 is 0, so p0 is going to be 0. That means the point of the curve is not going to be here, it is already going to be somewhere else, plus t is going to be 1 into p1. So whatever is the end value of coordinates of p1, that is going to be the equation value. That means it is already reached at the end. So that is why this equation is going to be correct, and we are going to have always the value varying, t value varying from 0 to 1. Okay, so as we vary the value for 0.1, 0.2, 0.5, 0.7, the equation can be, the L0 value can be found out. So here we can see in the video, as the value of t varies, the L0 position is going to move along the path and reach the final point, that is P0 in this case. Okay, so thereby it is going to be a linear equation. Okay, so if you take a look at this, two control points are there, but the equation has got only single degree of freedom, or single, it has got no square roots, squares or cubes and all, only single degrees. Okay, so that is why it's a linear equation. Now we'll go to the next one, where we have three control points. Okay, P0, P1 and P2. Okay, in that case we will have a quadratic equation. So the first thing is for this line L0. Okay, right, and the second one is for L1, right? So we can take L0 is already there over here, it is already written in the previous step. Now for L1, we have L1 of t is going to be again the same thing, 1 minus t into P1 is the starting point over here, and P2 is going to be the ending point. Okay, so now we have to club these two equations, because on both the sides, as the value of t is going to vary, the L0 and L1 position is also going to vary, right? So if you look over, if you see here, t is equal to 0.28, L0 is going to be here, and L1 point is going to be here. So both of them are moving simultaneously. So we have to obtain a common equation for this. Okay, right. So that is what is going to be given as Q naught of t is going to be 1 minus t of L naught t times of t plus t into L1 of t. Right. So that we get a it in one single equation where we are going to combine these two equations. So you can see here Q L naught is over here and L1 is over here where T is going to be 0.28. So Q naught value is going to be here, right? It is not going to be any more on this line or any more on this line, right? So as we had seen yesterday, if we take up just a second. If we take up like this, I said in the previous class where it is going to vary and we are going to have the curves in a different representative manner, right? So first it will be here, so then the second point will be moving here, then the third point here, and finally here. So ultimately when it goes, we are only going to get a curve like this, okay, right? So that is what, so tracing this curve is nothing but this Q naught position at every instant of time where the T value varies. Okay, so let us continue with this. So you can see here as the value of T varies, yes, the Q naught is going to be traced, and just now if we see at this, it is just moving accordingly this particular manner, right? Okay. So yes, so once it is 0.59, 0.85, Q naught is here. It all started over here and it's taking a turn here itself. So if we trace this Q naught, it is going to be in this particular curvature manner. So this curve that is obtained based on this particular equation is nothing but the Bezier curve that we are going to obtain. But it also depends upon one of the most important property. I'll just mention it now, which I'll be covering it later on. It all depends upon the equation. So this equation depends upon how many control points are there. So whether there is 2 control points or 3 control points or 4 control points. So depending upon that, this Bezier equation will vary, right? So here you can see that now he is going to trace the point Q naught average at every value of T that is going to vary, and then we are going to get this particular curve. Right, so this is going to be the path of the Bezier curve for this particular 3 control points. Okay, right. So next we shall see about, so when we do this, so we are going to get this particular equation. Q naught of T is equal to 1 minus T the whole square P naught plus 2 times 2 into 1 minus T, bracket is closed, T into P1 plus T square into P2. So if we put this, then it's easy to track all these things in one go, right? So this is going to be equation for quadratic. Okay. So next we'll see about for a 4 control points. So P0, P1, P2, and P3. So just now we have done it for 3 points. So there, now what we have is additionally we have, now here we have L0, line 0, line 1. Okay, here we have line 2. Right, so it is indicated by L0, sorry, L2 of T, where the value of T varies from 0 to 1. So it is again going to be a straight line if we consider only this. So we're going to have the starting point is going to be P2. So 1 minus T into P2 plus T times P3. Okay, so that is why this equation is written. Now, the next thing that we have to do is that we have to trace all of them simultaneously for every value of T. Okay, right? So for that, we are going to have Q0 and Q1. So Q0 is going to be here already for this portion of the curve that is going to be formed, and Q1 is going to be for this portion of the curve starting from the control points P1, P2 and ending at P3, right? So we have tracing to be done in this portion Q0 and tracing to be done in the other half, which is denoted by Q1. So Q0 is already written. All we need is now Q1. So Q1, we can take the same Q0 equation, but we have to replace it with the respective line terms. Okay, so Q1 of t is going to be 1 minus t. Instead of L naught, here it is going to be between line L1 and L2. So L1 of t plus t into L2 into t, right? So that's how we are going to get this equation. And then what we have to do is that now we have Q0 and Q1. Okay, so now what we have to do is that we have to combine these two equations. Okay, we have to combine these two equations so that we will be able to trace the path. Now, if you look at this, Q0 is over here, Q1 is over here, right? So if I just take up like this, so now it is still here, but this has started to move along this particular path. Okay, now I'll just continue that. Sorry. So now if I redraw it, from here, this portion has been moved here and this has moved here. But over a period of time when t reaches 0 here, but over here in this region, it has to be joined where it has to merge. Okay, so it has to merge. So thereby it is going to take a turn like this. Okay, so we will see that. So okay, right. So we have to combine these two Q0 and Q1 equation to find the common path. Okay, so which is where we are going to combine. It is going to be denoted by C0 of t. Okay, right. So C0 of t is going to be where between these two, what is going to happen is that now they're going to join the line. Here we have what? Q0. Here we have Q1. So it is going to be continuously varying like this, where this point is going to, this is going to be considered as one more line. So that is why this blue color line is going to be indicated. And for this, what is the value of C0? Okay, with respect to t is going to be calculated using the weighted method. Okay, right. So for this, all these things, interpolation has to be done. We have to interpolate these values to get the curve. Okay, so that is why these steps are being done. Okay, now as the Q0 and Q1 is going to move, this line is also going to deflect or move or is going to trace, and the weighted CO value is going to flow along the path along this line C0. Okay, we will see that now. So if you look at this now, here itself it's taking a turn, but after this the C0 is going to go any more over here because the line is going to trace a path like this. Okay, right? So it has almost become straight over here and it has crossed this. So this C0 is not going to go to P2, it is going to move towards P3 because that is the end point of the curve, right? So here it is now moving towards P0. So now if you trace the curve, okay, along the C0 value by having the t value substituted, the values that we will get is going to be like this, the orange color line, right? So the curve when we have 4 control points is going to take such a shape where these 4 control points is placed in these particular places. Okay, if the control points are shifted, then the shape of the curve will also vary, right? So ultimately when we put this together in terms of P0, P1 and P2, okay, when we expand this, it will be 1 minus t into to the 1 minus t the whole cube, P0 into P0 plus 3 times 1 minus 2 the whole square plus into t P1 plus 3 times 1 minus t into t square plus P2, sorry, t square into P2 plus t cube into P3, right? So that is going to be the expanded equation for these 4 control points. Now if you look at this, when we have 4 control points, the degree of the polynomial is going to be 3. So it is nothing but 4 minus 1 is going to be 3. So that is why it is going to be called as the cubic curve, or the which is based upon the cubic equation, right? Okay. So how this equation is going to vary is actually one of the property of the Bezier curve, which is nothing but it actually depends upon the number of control points. Now without any tracing, now we can see only the curve with respect to this particular equation, right? So this is how the Bezier curve is going to be formed, for which the mathematical calculation is required using the Bezier equation, right? Yes. So these are the things that is for our understanding of the Bezier curve. Okay. So now the first thing, the properties of the Bezier curve. Now we have seen 2-3 cases. Okay, right? Now let us understand what are the properties of the Bezier curve. First thing is that the curve depends upon the number of control points, whether there are 2 control points, 3, 4, 5, and so on, right? Okay, next, the next property is that the curve passes through the first and the last points of the curve, irrespective of how many control points are there. No matter whatever it is, the curve is always going to start and end on the starting and ending control points only, not on the intermediate points. It is not going to touch. Okay, next, the third property is that the polynomial of the curve depends upon the control points, as I just showed over here. So whether the equation is going to be in cubic or quadratic depends upon the number of control points that we have. Okay, right? Okay, right. So these are some of the properties of the Bezier curve. Okay, now we see that for the Bezier curve, the equation is changing with respect to number of control points, for which we can write a common equation. So irrespective of how many our control points are there, it can be used. The equation can be used. So we will see that how to make a common equation for all these cases. Okay. So yes. So actually, Bezier curve was actually is a name. Bezier is a name of a French person's name who was working in a Renault company, and he was the one who found this curve equation for use for surface modeling. Okay, and so thereby this type of curves are called as Bezier curve itself. Okay, right, and the effects of the vertices are weighted by the corresponding blending functions. That is the Q and Q naught that we just saw, right? And blended as in the Hermite's curve. So we have another curve which is called the Hermite's curve, which we'll see later. So the properties of this. So the curve passes through the first and the last vertex of the polygon. Okay, whether the that is the points P0, P1, P2, P3. Wherever it has been situated, it is always going to pass through the first and the last only. Okay, the tangent vector at the starting point of the curve has the same direction as the first segment of the polygon. Okay, so it's going to be in the same direction in the first segment of the polygon. Okay, and similarly, in the last segments also, it is going to give the same slope of the tangent vector at the ending point. This is because it at the starting and the ending vertex, okay, that is the first and the last vertex of the polygon, it is going to be, it has to pass through, it has to touch that vertex. Okay, right? So thereby there is no other go. So what he means to try to say over here, there is going to be a tangent that is going to be drawn with some vertex. Okay, and with this vertex, and there is going to be a tangent that has to be drawn over here. So it's almost going to be the same itself. So this is not going to be varied. But whereas you see that we can't say there is any kind of tangent over here, right? So it's not that easy to be, right? Okay, the values keep on changing over here in between depending upon the control points. Okay. So the next thing is that the nth derivative of the curve at the starting and the end point is determined by the first or the last vertices of the polygon. Yeah, right. Okay. So this is nothing but, as they have just mentioned it in the other way, right? So we can just easily remember that if we have 4 control points, then the degree of the equation is going to be in the cubic form, n minus 1. Okay, right. So the same curve is generated when the order of the vertices of the polygon is reversed. Okay. Now, say for example, now in this particular case, if I take, now if I take that this is P0, P1, P2, and P3. And now if I start using the Bezier equation to solve this, then I will still get the same curve only. Whether if I take P0 over here, P1, P2, P3 over here, I'll still get the same curve. So even if we reverse the order also, the shape of the curve is going to be the same. There is not going to be any change unless and until the control points are shifted. Yeah. So with this, by using the Bernstein polynomial function, okay, where we can write it as the equation, okay, with the starting is by this, where here they have taken it from I to n, nothing but the value of t is going to vary from 0 to 1, right? So what is the lower limit and what is the upper limit? Lower limit is denoted by I, upper limit is denoted by n. So it is going to be u to the power of I into 1 minus u. Okay, here instead of t they have taken it as u. So in the video we had seen it in the terms as t over here. Okay. All right. So next, where I to n is going to be factorial n divided by I factorial into n minus I factorial. Okay, where this equation, okay, when we start solving this, when we start doing the blending function, okay, and apply to the vertices of the polygon, in short, we can go in like this. P of u is going to be equal to sigma, okay, because in whether it's quadratic equation, cubical equation, we saw that it was the summation. So sigma I is equal to 0 to 1, okay, that is the range of I is equal to 0 to n, where the range is actually varying from 0 to 1, okay, in brackets I to n, okay. So here we have, it is we can either use the term T of I or U of I. Okay, in the video we had seen it here as T, okay, right, and into 1 minus U, or as per the video if you go, it is T to the power of n minus I, okay, n minus I, okay, into Pi, where Pi is the position of the vector of the ith vertex, okay, right, that is the starting, okay, that means P0, nothing but P0. Okay, these vertices are called the vertices of the polygon obtained by connecting these vertices. We get the control point. So Pi is nothing but P0, P0, P1, P2, P3, because it varies from I is equal to 0 to n. So this range I value is going to vary from 0, 1, 2, 3, 4, and so on. Okay. Yes. Yeah. So yes. So where n indicates the highest degree of the term. Okay, that means how many control points are there. Okay, based on that. Okay, the highest degree of the, not the control point, sorry, the degree of the polynomial. Here they have gone in the other way. Okay, right. So here what they are telling is the value of n is nothing but whether it's going to be quadratic, equation or cubical equation or fourth degree and so on, which depends upon by the curve defined by n plus 1 control points. So n plus 1 control points. If I have n is equal to 2, that is the quadratic equation, then control points is going to be n plus 1, that is 2 plus 1, 3 in this case. So we are going to have 3 control points. Okay, but in the video we have gone in the reverse manner. So if we have the curve, we will find out how many control points are there. Control points are 3. Then what is the equation for degree of polynomial for the equation? Then it is going to be n minus 1, that is going to be 2. Right? That's all is the difference between the video and this equation that is written over here. Yeah. Right. Now, say for example, for fourth disk properties. Okay. Now we have to show that it has to the properties that has been defined is going to satisfy the is going to be as per the equation that is going to be written. So the equation form should be correct and should satisfy the properties. Okay, right? So now if we expand this, from value 0 to 1, okay, in the equations 6.16 that we have just written, where P of u is equal to 0 to n into 1 minus u to the power of n P naught plus 1 to n, right? So this is the first step. Okay, this is at the starting. Okay, this is at the first step. The line has just moved by an incremental value. Okay, where u into n 1 minus u to the power of n minus 1 P naught, and next at 2, 3, and 4, and so on. This polynomial equation continues. Now, if we start substituting the value for P naught and P1, where u value is going to be 0 in this particular equation, okay, then what is going to happen? So when we substitute, u is going to be 0 here, this is going to be 0, this is going to be 0, here it's going to be 0, right? So once this has been multiplied by 0, this is going to be 0, this term is going to be 0, right? Because here we have u square. Okay, 0 into anything is 0, 0, 0, 0. So all we have is only 1 into P naught. Okay, so that is why we are going to get this. Okay. Now next, when we have the value of u to be 1, and we are going to substitute in this equation, then what are we going to get? So u is going to be 1. So 1 minus 1 is going to be 0. 0 into anything is 0, right? Okay, and similarly, so here we are going to have 1. This is going to be 1. Okay, n. Okay, so here all these things are going to be cancelled, and ultimately we are going to get only Tn when we have the value of t is going to be 1. Okay, or in this case, u is going to be 1. Okay, so that means what is this going to say? When we have t value is going to be 0, the point is going to be on the starting vertex. When you have the value of t going to be 1, the point is going to be, the point of the curve is going to be on the last vertex, which is denoted by p of n, the point, the vertex of the nth point. Okay, so thereby, if you look at this equation satisfies the first property, where the curve should always pass only onto the first and the last vertex of the polygon. Okay, right? So it satisfies over here, right? Yeah. So we'll stop here for today, and we'll continue in the next.